So if I'm understanding you correctly, there are various features of quantum theory that I mentioned earlier, such as superposition, entanglement, and interference, but there are others like Bell correlations, and maybe 4 more here, or 20 more, whatever.
Yep.
The point is that you then wonder, okay, of these features that we think of as being non-classical, can we develop a classical theory that triggers some of them? And you have found, yes, for interference, entanglement, and superposition. Yes, the answer is yes.
Right.
But you have not been able to find it for Bell correlations and so forth and so forth. And then I heard you say, or I thought I heard you say, that we have shown that you can never recover some of these fingers here that I have on screen classically. But it sounds to me like the latter part of what you're saying is that we just have not found a point that can actually recover them. So one is that there doesn't exist something versus that we have not found it.
So it's the first one that it doesn't exist. So the key is that we're showing that something can't be explained under some set of principles, we're proving a no-go theorem. So you might say take the conventional framework for realism, which I like to call the ontological models framework. It's about hidden variables, Bayesian probability theory, that sort of thing. Assume something called local causality, which is Bell's way of talking about things being local. I like to think of it in a causal model. There's only a common cause between the two wings of the experiment. Relative to those assumptions, you can prove that the only correlations you get will satisfy certain inequalities. The quantum formalism violates those inequalities, so you can say, right, I now have a contradiction from those assumptions. And so I know that one of my assumptions has to be wrong. So it might be the local causality, and a lot of people say that was the wrong assumption, that actually there are superluminal influences going on. That's what's innovative about quantum theory. But I'd rather say no, it's still a common cause explanation, but it's this conventional framework for thinking about realism, for thinking about causation and inference. That's what's going to change. But it's not that we don't know whether there's some model that can reproduce this. It's rather we've proven a theorem, right? So there are certainly models that can abide by the conventional framework for realism and violate Bell inequalities. It's just that those models run afoul of Leibniz's principle, and so that's why I don't care about them, right? So let's say I try to build a model that really has superluminal influences in it. So that's how I explain what's going on in a Bell experiment. I say, okay, the set, we have Alice and Bob. That there's a pair of particles that gets prepared at a source, and each one gets a particle. And then Alice has a setting variable that determines what she's measuring and an outcome, similarly for Bob. So if I allow Bob's outcome to depend not only on the physical state of the particle he got and the setting variable, but Alice's setting variable as well, right? So that would have to be a superluminal influence because they can do these measurements at space-like separation. So that influence is going to have to go faster than the speed of light. If I allow that, then yes, I can explain the Bell inequality violation. Okay, but why should we be dissatisfied with this? Well, the usual story you hear is, people who trust relativity say, well, it just feels like relativity is not merely saying that signals can't travel faster than the speed of light. It's saying that influences can't travel faster than the speed of light. So you might just say, well, that seems in tension with relativity to say that there could be an influence that travels faster than the speed of light. But you can do better than that. And you can just say, look, if you believe in Leibniz's principle, then this is clearly not Leibnizian because, imagine, Einstein's elevator thought experiment. I go to Bob's lab and I do every experiment you can imagine looking to get some information about what Alice's setting was. And lo and behold, no matter what I do, according to relativity theory, because they're space-like separated, and there's no signaling, nothing I do in Bob's lab can teach me anything about what's happening inside Alice's lab. So what I do in Bob's lab can't teach me about Alice's lab. So at the empirical observed phenomena scale, there's no evidence of any influence, no signals for any experiment that you could do. But to imagine that there's nonetheless an influence, well, that's violating Leibniz. That's saying that there's an ontological difference, but you cannot see it, right? There's no experiment you do will see that difference. So that's the sense in which Bell's notion of local causality follows from Leibniz's principle. And that's why, I would not want to give that up. So it's the conjunction of Leibniz's principle together with this conventional framework for realism that leads you to contradiction. And so that's the sense in which I could say, look, there's a certain kind of, there's no toy theory-like construction, that it'll satisfy Leibniz, it'll be in this conventional framework that's going to reproduce the Bell inequality violations. That's clear. Now, more generally, that's my take. But more generally, what I'd say is, in quantum foundations, it is good to follow this methodology of no-go theorems, right? So, like, if we just argue about, oh, I got this model, I want to call it classical, I think it's nice. If I look at like what Feynman wrote about things like interference, so Feynman famously said interference is the essence of quantum theory. So some of my work showed that, well, that's just not true. Like I can reproduce. Feynman said there's absolutely no way to reproduce this classically. I say that's not true. I can have a classical model, reproduces the phenomenology. And the problem with what Feynman said was that he didn't prove a no-go theorem. He didn't say, this is what I mean by a classical explanation.
Right.
Principles. Here are the predictions of quantum theory. Here's the contradiction. If Feynman had done that, then all we could do in response is maybe dispute those assumptions. We might say, well, that's not how I think about classicality. So I think we escape the contradiction by giving up assumption one. And that's what's so nice about the methodology of no-go theorems in quantum foundations. Like we all, researchers in quantum foundations, tend to disagree about what the fundamental principles are. But what's great about a no-go theorem is that if you agree that it's a logically valid argument, you have to say which of the assumptions or many of the assumptions that you disagree with and why. And so it focuses your attention on the principles and how should we articulate these principles and are they reasonable or not. So yeah, that's the sense in which somebody could always say, all right, you've proven a no-go theorem, but here's why I don't think it's very significant, because I think the assumptions you put into it aren't natural assumptions. So most people agree that Bell's assumptions and Cauchy-Specker were pretty natural in some sense, and so those no-go theorems are significant. But other no-go theorems might not be, because they're built on assumptions that are just not natural, that nobody really thinks are plausible.
Can you explain to a mathematician what is special relativity, such that the mathematician may say something like it's invariant under SO13. Some theory that's invariant under that. Now, of course, there may be more conditions, but either way, once you've specified what special relativity is, what the heck is the difference between something being non-locally influenced and then some people will say, well, special relativity allows non-local influences. It just doesn't allow you to communicate non-locally or superluminally. Right. Where is that said in special relativity? Like, explain to a mathematician.
Yeah. I mean, if you take, say, Maxwell's theory of electrodynamics, then it's sort of clear that you have neither any superluminal signals nor any superluminal influences, right? So it has the Lorentzian symmetry, it has the right symmetry to be consistent with special relativity, and it has neither of these features. It's only when we start asking about quantum theory, characterized totally operationally, where we're like, okay, well, we just have these statistics of outcomes of experiments. And, what Bell asked was, is there any picture of reality, could be Maxwell's theory, it could be Field's, it could be anything. I don't care what the underlying theory is. Is there any theory that respects the following aspect of relativity, namely that influences do not propagate faster than the speed of light? So he was assuming the structure of space-time that's in relativity. So I can find two regions that are space-like separated, meaning that there's no influences between them. That's what you're stipulating. That if you imagine that all influences have to propagate within light cones, then I can find two regions that are outside each other's light cone. I can use that for the Bell experiment, right? The settings on Alice's side are outside the future light, outside the backward light cone of Bob's outcome, and therefore, if I believe that influences subluminal, there can be no influences there. So it's not the the full apparatus of special relativity that's appealed to in Bell's argument, but rather just this aspect that says there is a fundamental speed limit, and therefore there can be two regions of space-time that are not ordered causally. Right? They're sort of causally disconnected. That's the only thing that Bell's really using in that argument.
Okay, what's meant by influence? And is influence the same as causal influence?
Yeah, I've been using influence to mean causal influence.
Is there such a thing as a non-causal influence? Like
No.
help me understand what
Yeah.
influence means.
Influence, just a good word to talk about a cause-effect relation. So, variable X influences variable Y. That means that, X is a cause of Y. So so far in our discussion, I've been trying to distinguish influence from signaling, right? So you could say, maybe here's the best example to see how they really come apart. They're not the same idea. It's from cryptography. So okay, let me get there in a moment. So what's the way in the field of causal inference that causal influences are mathematically modeled? You can think of it as just its functional dependence. So the key is unscrambling this omelet of inference and influence. And so if I think of like projectile motion, right, I can write down a formula that relates, say, the maximum height of the cannonball, the initial velocity of the cannonball when it came out of the cannon, and the angle of the cannon. So I can write down a formula that relates them. And if you give me any two of those variables, I can infer what the value of the third is, right? So I can say, oh, you give me the maximum height and the angle, I'll figure out what the velocity must have been. So that's undergraduate physics. Allows me to write that equation and solve for any of the three variables. But the only one of those equations that really describes a cause-effect relation is the one for the maximum height in terms of the velocity and the angle, right? Because if I modify the initial velocity or modify the angle, that will impact what the maximum height is. But if, the cannon has been shot and I go and I move it up a bit, well, that's not going to influence the cannon. So we all kind of intuitively understand the asymmetry of causation, right? The inference is symmetric. I can make inferences between lots of different variables, but causal influence is asymmetric. Another good example would be if you think about the rooster crowing and the sun rising, there's a correlation there. So you might say, okay, well, what's the causal relation? Well, if I make the rooster crow in the middle of the night, it doesn't cause the sun to rise. But if I move the rooster eastward on the earth so that the sun rises later, it crows later, right? So I can figure out what the causal influences are based on interventions. But also our theories of physics teach us something about, what are the causal relations, like in the cannonball example. So effectively, causal relations are described by functional dependences, but they're very specific functional dependences, right? Because inferences can also be functional dependences. They're functional dependences where we imagine that if we, say y is a function of x, and were I to vary x, y would vary. That's effectively a causal influence. Okay, so now why is that distinct from signaling? So here's the example. It's from cryptography. So there's something called the one-time pad in cryptography, or it's sometimes called the Vernam cipher. So say I have some plain text, some sequence of bits, zeros and ones, and I want to communicate them to you. And we share a key, so some secret string of zeros and ones. And that key has been generated at random from all possible sequences. Then I can add the key to the plain text, send it out. That's the ciphertext. When I add them up, mod 2, send it out in the open. Mm-hmm. You get it, you add the key, you get the plain text back. So in the simplest example, I'm sending you one bit, that's the plain text. The key is just one bit. I add them together, mod 2, that's the ciphertext. Now, the way this is designed is that the key is sampled at random from a uniform distribution. It's either 0 or 1 with equal probability. And therefore, the ciphertext, if you say, well, what do you learn about the plain text? Well, if the key was 0, then the ciphertext is equal to the plain text. And if the key is 1, it's just the flip of the plain text. And the eavesdropper gets the ciphertext and says, my estimate of the probability of the plain text being 0 is a half, and the probability that is 1 is a half. And so the eavesdropper has exactly 0 information. It's just as if you were guessing, right? So the information, theoretically, they learn nothing about the plain text. That's the whole purpose of the protocol. Now, if you ask about signals, right? So say I vary the plain text, and I say, well, what's the distribution over ciphertexts that results from that variation? The ciphertext is always uniformly distributed 0 or 1 because the key is uniformly distributed 0 or 1. So it's equally likely to be 0 or 1. And if I am sending a different message, it's also just going to be the uniform distribution over 0 and 1. So that's an instance where there's no signal from the plain text to the ciphertext. Okay. Changing the plain text is not going to change the distribution of the ciphertext at all. That's no signaling, right? There's no change in the distribution. But of course, there's a causal influence. Because if there were no causal influence, there'd be no way that the recipient, could decode the message. There has to be causal influence. So the Vernam cipher shows you that there can be causal influences where you kind of wash out the influence. You don't get to see it because you've sort of added noise. So signaling is stronger than influence. It's like, oh, there's an influence, and furthermore, it's not being washed out by a noise source. But I can have influence with no signaling. So that's the sense in which they're different concepts. And so in Bell's theorem, when you look at models like Bohmian mechanics and other invariable models that manage to reproduce Bell inequality violations using superluminal influences, they use exactly this trick that they sort of wash out. They say, well, we have influences, but we can't use them to signal. Why? Because we're sort of washing out the influence by adding local noise. So it's the Vernam cipher trick happening in all these invariable models. That's how you make it consistent that there's no signaling and yet influence. And so that works fine, unless, of course, you want to stick to Leibniz's principle, in which case the fact that nothing you ever do can see that signal means that you should not be assuming that there's an influence there.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.